Let's get started. People can keep rolling in. My name is Jason. My co-presenter is Nick Flesher, our
Hello, everyone.
Director of Engineering. Today we are going to be talking about how to get started with laser plastic welding. A couple things to get straight before we go. As you can tell, we have a chat. We're trying to make this very interactive. So if you have questions, comments, please use that. We're going to try to interact with you through that as much as we can. And hopefully everybody will keep tracking. So if we're saying something and you're not sure what's going on, please ask the question, because there's probably other people in the room that also are wondering it. Maybe we just misspoke, maybe we didn't make it very clear. So as I said, I'm Jason Dornbos. I'm going to get actually started with the next slide here. So before we get into the depths of laser welding, I wanted to quick point out where we're coming from at Xtol. So we are a company that makes manufacturing technology. And on the slide here, you can see a bunch of the different example technologies. So we invented infrastake and nanostake and the rapid conductor. We are talking about laser welding today. We have a kind of a different approach to laser welding, which we'll talk about. We have spin welding. We invented infraguide, which is an infrared non-contact IR welding process.
Those who don't like IR.
Yes, it's for those who don't like IR welding, because it's got some significant advantages over traditional IR welding. Namely, you're not going to light things on fire. 3D printing, we use HP's multi-jet fusion 3D printing technology, and so we sell parts and tooling and prototypes. It's a production grade 3D printing technology. And then, of course, we also do custom automation, and that is our bread and butter. So we take all of these technologies and we automate them. And we take them from different levels. So whether you want just a standalone machine, something fairly basic, the operator stands in front of it and puts parts in, or you want a fully automated cell that you never touch the parts. It comes off the injection mold, goes into the automation cell automatically, and literally leaves the building on an automated guided vehicle. We can do that too. So we'd love to talk more about what we do with you as we go through this, but now I'm going to hand it over to Nick, who is going to talk more about laser.
Great. Thank you, Jason. As we get into this, if you've attended one of our webinars, you know that we want interaction. If you have questions along the way, please just pop them into the chat. Jason will pause me if I really get on a roll. We want this to be live, and the best way to add value to whatever application you're thinking about, you might just be learning a new technology that you don't have an application for yet. You might have a live one, and we'd be happy to go into that in the webinar here. So at the end of the 20 or 30 minutes or so, we'll have question and answer. Hopefully we've got some good questions along the way maybe we didn't address. And then Jason and I's contact information. Feel free to reach out and we can go deeper. But let's go ahead and get into it. We want to talk sort of entry-level baseline information for laser welding. We've got a couple more webinars on our website around laser welding specifically. Designing for sort of our strategy on how we configure lasers. We've got some pieces of that in this webinar today, but before we get into the technical aspects of laser welding, we just want to talk about how Xtol got into this and why you might choose Xtol versus maybe some other folks.
Juan, is that better? Nick sounds a little bit far away. My computer's the microphone, so we're just going to do this.
Just going to push it a little bit. Is that better, Juan? Thank you so much, Juan, for bringing that up.
Also, Robert just quick meant same material compatibility for the two sides on infra welding. Yes, the materials need to be compatible with each other in order to weld them together. And typically, material compatibility is similar for the different welding technologies.
That's right. Yep. Good call. So hopefully, if you guys can't hear me, feel free to jump in there in the chat, and Jason will make a change on the fly. But the slide you see here is just a graphic to sort of show what we sort of perceive in the market. Standard laser welding machines. There's a couple companies that do that, and then there's other just off-the-shelf components that machine builders might be able to put together. We say there's a big gap in the market. We try to bridge that by having a configurable solution around your application. That's kind of one thing that we do throughout all of our technologies, but is really important to make sure that you've got the right solution. So the process itself is pretty straightforward. There's 3 overarching steps. There's nuances, of course, to all of that. But essentially, 2 parts, usually 2 parts get clamped together. We heat those components with a laser beam, which is, we'll get into a couple different methods for that in a moment. And then we cool it together. So that's it. It's a 3-step process. We'll talk about process parameters, and we have 3 key elements to laser plastic welding that you have to have for laser welding. And actually, I'm not sure if it was Robert mentioned, compatible materials is number 3 there. So we have compatibility charts. I don't think we have that in this presentation today,
But we have it on our website.
but we have it on our website. And so for specific for laser plastic welding, which as Jason mentioned, is pretty similar to other welding technologies. First one is intimate contact. We do that with a couple different methods. One is tooling design. There's a few tricks that we do for tooling design to make sure we've got good intimate contact. We'll talk about why that's important in just a moment. But that's crucial. The second way that we do that is making sure we've got good part design, making sure things like ejector pins aren't on the weld surface. So our applications lab can kind of help you with some of those part design specific items. The second is really important, and that is IR transmissivity and absorptivity. So whether you're talking about 1 micron or 2 micron laser welding, which we'll explain here shortly, it's crucial that you have the infrared wavelength that we're using for laser welding to be able to transmit through that upper part and be absorbed into a lower part. And not all colors that you might see would be absorptive and transmissive. So we can help you with that. Just to kind of see visually what those 2 previous slides look like. This is a video that I'll play a couple times in case any questions arise from it. See, this is in one of our lab systems. It's using flat glass. Typically, we try to use an aluminum clamp, but just for visual effects here, we're clamping and getting that intimate contact with just a flat glass. And you can see that being laser quality. This is actually a 3D printed part we did with a piece of sheet stock just to showcase a couple different technologies in one. That's a prototype tool, not a production tool, I would say. And so again, that 3-step process, we clamp, we're applying the laser energy, which we have to use the proper filtering in our camera to make sure you can see that optically.
Yeah, because otherwise you look in there and you don't see anything.
Yeah, in the normal 1 micron or 2 micron, you don't see anything. It's invisible to the human eye. Let's go ahead and play it one more time. We're using quasi-simultaneous laser welding here. Again, a lot of previews here that we'll talk in more detail in a moment. Cooling is happening there.
And we also have to add the sound effect.
Yeah.
Because it
right.
doesn't do that either.
Yeah, you gotta.
Does the cover have to be clear?
Great question. So it has to be clear at the wavelength at which you are welding. So in other words, and you'll see this in about 5 slides, you'll see an optically opaque material that looks black to the human eye, but is transmissive to the wavelength that we're using. And that wavelength is here. So there's different wavelengths that we use. 980 nanometer is the specific wavelength we use, which is commonly called 1 micron. And that heating method happens because we're absorbing energy into the lower component, and it conducts the heat into the upper transmissive component. So the heat transfer that's happening is radiation and conduction. If you don't have good intimate contact, there is a good chance that you won't have good energy transfer, and you can actually see a little bit of burning in some cases. So it's really important that you have that intimate contact, because as this visual shows, that's what's doing the heating. 2 microns, another wavelength commonly used in plastic welding. We have both of these laser sources. And this is a bit different because you're using a combination of a couple things. One, you can do clear to clear because part of the energy is absorbed into the upper component and part of it is absorbed in the lower component. The rest of it is lost. That's what this graphic kind of shows here. And so you get a higher heat affected zone. So if our laser beam spot, let's say for instance, is 3 millimeters, you'll get a millimeter usually, give or take, on each side, depending on the thickness. The second thing that's important to note about 2 micron is the focal point matters a lot. So you can kind of see this beam on the upper side is converging. It's coming to a little bit to a point. This length in the laser space is called the Rayleigh length, and it's almost like a collimated beam at that point, and then you see it diverge as it goes outside the back. So for smaller parts, this is pretty straightforward technology because we can keep that focal point throughout the XY geometry of the part. For larger parts, you might need to use a 3D scanner that adjusts the focal point as you're going through XY profile.
And just for clarity's sake, that graphic on the right almost looks like we have 2 lasers pointing at the part. That is not the case. Laser
Correct.
comes from the top.
Yeah, good point.
And then it's going out the bottom because it's not being fully absorbed.
Yeah, good point. Yeah, so what you see here is the laser beam's coming through the top, about 30% is absorbed in the upper, 30% of the energy is absorbed into the lower, and 40% is being lost through the part. Usually you don't see heat effects on maybe you've got a back end of a part or the tooling. Tooling might get a little bit warm perhaps, but it diverges pretty quickly and that energy is lost. So 2 different methods. 1 micron, kind of on the left, uses conduction. Very, very precise. You'll see some images here in a minute where the heat doesn't really migrate outward because it's fast and it's absorbed. And then the 2 micron where we're using some of that transmission through both parts.
We got a couple questions here, and I can answer some of these.
Yeah,
so
great.
First, the welding video, yes, that was real time. It was not sped up or slowed down. That's the speed. The laser beam, the speed at which the laser beam traces around the part, that's settable. Like you can slow it down, you can speed it up. It can go a whole lot faster than what it was in that video. Do we do any inline testing during welding?
I would say it's not typically. You'll see, for sort of customers and proprietary reasons, we've got a couple of designs that you'll see later. We have done a little bit of vision, but that's outside of the weld area. There's in theory, we could use some vision while the weld is happening and continue to advance. We usually weld by depth if we can, and therefore you're allowed, you're giving some quality parameters back that says I'm meeting my certain force requirements, I'm advancing the weld as I'm putting the energy to it. That's typically all we need. But leak testing after the weld, vision are 2 commonly used quality items. Good question, but not currently.
So we got 2 other ones. How does the cost of this method compare to other welding methods? Hot plate welding, infrared, ultrasonic. We might get into that in a little bit.
Yeah, I think, Tom, let's hold that question for now. Let's continue on with the theory. That is the question that most people want to know. And we're not bashful about that. It does cost a little bit more than some other methodologies. But we'll talk about 3 things to watch for here in just a moment that says, okay, maybe laser welding is the right thing.
Yep. Another one, this is an interesting one. The laser welding video, was it making a wider weld rib, or was it just tracing the same exact path?
Yeah, that was tracing the exact path. And that was actually quite a weld. We do much more precise. I'm going to skip ahead, Jason, to slide 9. I think this might shed a little bit of light on that question. And great questions, you guys. More coming in here. One from here. It looks like define clear a little bit more.
Yes.
Yeah. So let me go ahead and answer that one, then I'll get back to the multi-pass question, which is really good. Keep these coming, you guys. This is fantastic. So clear. When I say clear, it's usually clear opposite of what I was saying, optically, right? So and actually technically, I guess, to the wavelength as well. So oftentimes when we see the need for 2 micron, it is optically clear parts. We have seen a couple applications, not produced equipment for, but couple of applications where optically it was opaque, and even really to 1 micron it would be transmissive, but the applications required that we have some 2 micron energy to absorb into both. And when I say clear, it can't, like I said, it can be crystal clear. It could be like a polycarbonate or a PMMA. It could be maybe a natural nylon. We see a lot of natural nylon. Some, in fact, dyed to the 1 micron transmissive wavelength that again appear black and optically, or sorry, to the wavelength is clear. So,
and in that video, the top, that sheet stock, that was natural polypropylene. So it's
right.
I mean, you can't really see through it very well. It's pretty milky.
Yeah. And in fact, I'm kind of bouncing all over the presentation, everyone. Apologize for that, but this slide is a nylon that we laser plastic welded. You can kind of see the weld joint. This has been sectioned. We're kind of trying to protect our customers' part design there a little bit. But you can see a natural nylon that's white. And we could do that just as well with black if the proper care was taken to get a resin that was dyed with 1 micron transmissive black dye. So that's kind of, we talked a little bit about the lasers. I want to get into, I was talking about multi-passes. Mm-hmm. So there's a couple different types of laser welding out there. Quasi-simultaneous is probably the most common that we see. We're essentially moving many passes along the weld rib with one beam. And you can use a variety of different weld joints. We say T-joints here, Jason, but that's not exactly the true. And we're simultaneously bringing the temperature of the melt rib up to temp. So that's why quasi-simultaneous, if we can do it, is usually the best. Contour welding is usually used for larger parts, maybe XY gantry, where the laser beam is is being physically moved, and it's got some benefits to size, but from a challenge standpoint, you can kind of see that beam goes around, and by the time the laser beam gets back to the starting point, it's cool. So you don't get this uniform advance of the part. It kind of needs to step a little bit. So this can be a little bit tricky to make sure you've got good intimate contact for contour welding. Line beam is just basically where we optically manipulate that beam and kind of like a paintbrush, as we say. This is good for microfluidics often and for kind of smaller parts in some cases. And then if we need to go less than 1 millimeter, masking is a good way to do that. Can the parts be filled? They actually can be filled, usually more than 20%. We need to start paying attention to thickness. So very commonly for, like, say, glass-filled PBT or glass-filled nylon, you get less than 2 millimeters. You can probably go up from a top layer. You can probably go up to 30% glass. There's a couple things. One, edge gating, if you're molding them with glass, can be a challenge because you can get a concentration of the glass at the gate. Two, it's important to not just edge gating, but just, I guess, generally make sure the glass is homogeneous, which is a tricky thing with molding glass. 20%, not usually a challenge. More than 3 millimeters of thickness, and it can be quite tricky. We can do contour welding, absolutely. Joint design, Tom, we have on our website, and actually, I think
we'll talk about it later.
We'll talk about it later, and we did a webinar specific to that, I believe.
Yes, we did.
So you can find that on our website. And just for everybody on the call here, it's super important for you to know that we have an applications lab that, in most cases, it's free of charge for us to just advise, collaborate, work with you on what's the best weld joints. I say most cases because if we end up using some laser time and prototype tooling, we might have a minimum fee for that. So use our website, check out the webinar, but please engage with us, and we'll be happy to assign you an engineer to get into that. Mm-hmm. Can the weld line be 3D? Not having the weld line on a flat plane? In some cases, yes. You need a couple things. One, more than a ½ inch or inch rise can be challenging. But sometimes that can be overcome with a three-dimensional scanner, like I mentioned earlier, where you're adjusting the focal point with the XY dimensions. So with that, I'm going to pick back up at mirrors. One thing that's important to note is you've seen quasi-simultaneous, you've seen on an XY plane. This is two different applications, let me be very clear. This is a mirror tool that did an oval part for the customer's sake, was not able to, not showing this part. But essentially what's happening is the laser beam is coming down, hits this angle, and comes in tangentially to the weld rib. Sometimes we'll do an angled rib for that. Sometimes it's an interference fit. So a lot of times, especially, laser welding's been around for quite a while, but we've seen applications with round or even oval parts like this where the part's getting rotated about the laser, and there's a couple challenges with that. One, you can only move the part so fast. With the laser beam being manipulated by the scanner, we can go 3,000 millimeters, 4,000 millimeters per second, which is a good process parameter to be able to pull that lever sometimes, and could just make you weld faster. So here's an example of a tool. It was kind of a unique shape. This is an actual part that we welded. This part's around 6 inches in diameter. We came down again at that angle. The laser beam is up above, bouncing off that mirror and going around the part exceptionally fast. So just keep in mind that mirrors might be able to do something you might not think is possible. And we optically engineer these. We've got design engineers that have software that helps them to do that, because it's not just a single point that the laser's coming from in the lens package.
And can I point out that we have heard from some people that you can't do it with mirrors because they've had bad experiences with other people that are, I'm not going to name names, other people that are trying to do lasers with mirrors. Yeah. And then they came to us and somehow magically we were able to do it. So it is possible, but it's not easy. We know how to do it, and we would love to help you do it.
Yeah. This mirror that you see here actually is one of those situations. So it's crucial that you've got a good surface finish, and it's super important that you engineer it properly and not just determine, well, I can get the laser beam to go where I need it to go to hit the part. That is not the right approach. It's important to make sure it's engineered properly. So we want to just talk a little bit about I think I need to use the cursor. Oh, yeah. So we're talking a lot about wavelength, and just want to pause for a minute, because if you go back into maybe a high school physics class or maybe some engineering courses you may have had, there's way down here ultra short gamma rays, and then there's radio waves that are all over in our air, over the airwaves right now. We're talking specifically about the infrared spectrum. Okay, so as you sort of zoom out from this spectrum, 1 micron I mentioned earlier, which I think is right here, and 2 micron is right here. So what we find is not all plastics are optimal at the wavelengths that we use, but it's pretty darn powerful, and there's different colors and different material types where they're more optimal at different, maybe say like 780 nanometer. That doesn't necessarily mean we can't use a 1 micron source. So just want to kind of get into a little bit of the physics, the wavelengths that are out there. So on to when you need know some indicators that say you need to use laser welding. Cleanliness, super important. No welding technology is flash free, but laser welding is pretty darn close. It does not produce particulate typically. I actually would say I haven't seen particulate. If you've done vibration welding or ultrasonic welding, you definitely have to make sure you've got sensitivity to maybe if you're welding with electronics or you've got really clean parts. That's not ideal. Laser welding is the cleanest that you can get. Oftentimes you get a visually appealing flash. If I go back to this slide, this was a show surface that we had where we were literally, it looked molded into the part. Looks like, Jason, we've got 5 minutes, so
we'll just keep motoring along.
Cruising along here.
Hopefully people can hang with us, because I think we're going to go long.
Yeah, no excess heat is another thing with laser welding. You don't have this heat migrating out. 2 micron, you do need to be mindful it's a little bit more, but it's a little more precise than hot plate welding. Precision wise, you can weld miniaturized parts and you can do it really fast. This part is smaller than a dime, and we're able to weld that in about 1.5 seconds with only 25 watts. I'll talk about wattage in just a moment. You can get really precise energy application, 0.7 millimeters, all the way up to 4 millimeters if you need it. What's more typical for us is around 1 to 2 millimeters. Fast, we talked about. You saw this image earlier. We've got other videos that sort of show this, but you can have, like I said, 1 second. Actually, I think we ended up doing like 1.5 seconds, a really small part. For larger parts, you might get up into the 10-second range. We usually size the wattage of the laser appropriately for the speed and cycle time that you need. Okay, so I've talked a lot about material types, absorptive, transmissive. You got to have the right compatible materials. We talked about that a little bit. IR transmissive material, as I said, it can be black. This is the same part. And what you see here is an inspection system where we're illuminating the part with 1 micron light with a 1 micron filter on the camera. So these are the same parts. You can see the weld rib underneath, just as if that top part was completely optically clear. Yeah. So filler materials, we talked about that some. It can impact the process. Just need to be mindful of that. With respect to process parameters, we'll kind of just touch on this quickly. Force, laser wattage, weld depth, the focal point of the laser in the path. Obviously, you need to hit the part, and number of passes and laser speed. Those are the levers we're pulling when we dial in an application. That weld depth is really important. We do sort of a closed loop control around weld depth, and it's totally application specific. We've had a really compliant part where we couldn't really use weld depth, but we used vision to make sure we had a good weld rib for that particular application. And usually depth-wise, we're running around a millimeter or so, give or take. If it's a really small part, we might be using 0.2 millimeters. That really small part was actually 0.2. So a lot about the technology, just a couple slides on how we do it at Extol. You can just see sort of 3 options here, more of a smaller footprint. This particular application, this CAD, has been out in the field for a while and is doing part marking, interchangeable tools, part reject if we don't hit, if it's not marked properly or if our weld depths aren't met. This is a operator 2-position dial where the operator can do the sort of cumbersome loading while the laser is doing its work. This is a completely automated cell that we have in process right now. So we really can look at whatever application and apply the equipment to whatever manufacturer needs you might have. How to arrive at this is kind of a busy slide, but just to show this is all that we're looking at when we bring an application in. We start with the parts. We maybe do some CAD work with you, some applications in our laser. We might be looking at some materials. Then as we transition to equipment, when the time is right, we look at power. That substantially drives the budget. We go 10 watts all the way up to 750 watts. We look at automation, like Jason said. Do we need a standalone? Over half of what we do is automation, so we can sort of look at what's required. Tooling features. What's your budget? How complex of tools do you need? Auxiliary functions. We see a ton of auxiliary functions. It's quite surprising. Compression limiter inserts, barcode scanning and printing, multi-cavity nesting, part marking, leak testing, vision inspection. So, Jason, did you have something?
No, I was just going to point out, like, we often get the question that, like, well, what's the wattage of your laser weld machine? That's not how we approach this at all. We don't have a standard laser welder out there. So if you need, like, what does the application need? That's what we always come back with what wattage, what does your application need in order to hit the right cycle time? What's the maximum force that you can apply with your laser welding press? Whatever the application needs, we will build the machine around that application.
Yeah, I think to that point, Jason, when you see sort of configuration, press assembly is a great example. We've literally put the force application in the tool itself because it was really ultra low, maybe 50 pounds of force. So you don't need a large press structure. We've had 5,500 pounds required for a really large part. So we don't have a standard size laser, standard size press. We make sure that we are sized properly because in our experience, that's the most important thing. The laser welding is really the laser is kind of the simpler portion of it. It's more around the part, how much force you need, your tooling, and the material requirements. I see a question.
Yeah.
Make sure we'll get to that, Robert. Thank you for throwing that out. We'll get some more clarity around that.
If you have to leave because it's 11:31, that's okay. This is all being recorded. We will send out a copy to all of you afterwards. But if you can hang on, we're going to keep going.
Yeah. So we touched on all these. So we've got just a couple more slides. The lens packaging, we won't really get into optics and how we do that work. Just know that that's something that we consider in our application. Tooling wise is really the most. We do have a patent pending technology called laser lock, where we essentially can do part pickup, which is could be a challenge with laser plastic welding. Control system wise, any platform that you might have, we don't have a standard that maybe doesn't interface well with your automation or your manufacturing. And it looks like
We made it.
we made it. We did the end. It's
Okay, so there's a couple questions that I wanted to make sure we got to.
Yeah.
That I wrote down. So we wanted to talk about the cost comparison.
Yeah.
Laser.
Yeah, let's talk cost. We like to talk cost. So I would say we'll start with there's a couple technologies. Cleanliness, right? I talked about cleanliness being really important. There is clean vibe technology that does IR and vibration and hot gas technology that I would say are on the upper end of the cost spectrum. For our laser welding solution, ours is quite a bit lower than that. I would say hot plate and vibration would come next. And then ultrasonics would typically be the lowest. The pros, you always have benefits, right? So it may cost a little bit more, but if you really need clean, go laser welding. If you don't, and the parts are small enough, ultrasonic might be the right solution for you. I will say that our applications lab, we do all technologies here. We may not make our own vibration or ultrasonic, but we know how to integrate ultrasonic. We do it through automation group. So we're not shy about maybe steering a customer away from laser welding. If you go to a laser welding company, you're going to get a laser weld. So I would just say that we have that conversation. What's your volumes? How big is your part? Is a surface marking a challenge? Because if it is, ultrasonic also might be tricky with that. So that's by far the cheapest. Up from there, vibration, again, cleanliness, how thick and beefy are your parts, because vibration is pretty aggressive if you've ever done vibration welding. If it's not tooled properly, you're going to have fractures and you're going to have pre-built stress in your part. Hot plate welding, we have a pretty sophisticated hot plate welder, but it's got material challenges. And then is laser welding, which does clean, does fast, does precise, but you have to have your material combination right, and you got to have the budget.
I'm just putting something in the chat that is a link to our material compatibility chart.
Great, thanks, Jason.
I'm also going to send a link to our design guidelines for laser welding. And I am going to pull those up. And whoops, I need to pull this. Hold on.
While you're doing that,
I'm going to take over the presentation.
Okay, go for it.
Hopefully it'll let me. Maybe it won't. No, I got it right here. Boom. Taking over the screen. Here's our laser welding design guidelines. So this is on our website. It's just if you go to technology, laser welding, and then you can find a link from there to get to these design guidelines. There's several different types of joints that you can use. And So, you know, we don't have dimensions on here or anything like that because it's all very dependent on your application, how much strength you need, you know, how big is the part overall. But these are the general like shapes and geometries that and these are not an exhaustive list. There's more than just these, but you can kind of get a good feel for what's possible. And then the material compatibility chart is down here. Something that I'm curious, I don't know if you answered this. The upper transmissive part should be approximately 3 millimeters thick or less for semi-crystalline materials, and can be much thicker for amorphous materials as long as they are transparent. Ta-da!
There you go.
So that information is there.
I do want to, Bob did ask, so we've got a couple questions that Bob asked us to go over material transparent again.
Yes.
We can use our inspection system. Right. So if you've done some development of your materials, we have a couple material companies that we work with and can guide you in that realm if you really determine that laser welding is the technology that you need. So we can share those material companies with you. We can inspect it, and then most often we try to shoot it with a laser. We make sure that even if we can get flat material plaques, and that's a free of cost, we just kind of work that into our lab schedule. So I hope that answered your question, Bob. It's 1 micron is typically what we see the most of. And if you have more questions beyond that, we can get deeper into your application, which I'm assuming we don't want to necessarily get into on the webinar here. It looks like we were asked,
can you weld 2 at once?
Yes.
Or two simultaneous?
Yes.
2 in the same tool, whatever.
We can. We have seen that it's not optimal to do 2-up multi-cavity tooling with 1 press structure. So we actually have a machine on the floor right now that runs 2 independent force control while we have 1 laser source. So it's a cost saving. You don't necessarily need to have multiple machines. You can use the 1 laser source, which is a little bit more of a cost driver, and run independent. And that also allows you independent process control, right? Like you can run a little deeper on one part versus another. Great. That's a great question.
There's a question about welding metal. That's not something that we're.
Yeah, that's kind of a different animal all to itself. We do have, Axtell focuses on plastics joining, plastic welding, plastic staking, and assembly. So I would not say we're the experts to that. We actually have done an application where we did some embedding of a metal component into plastic. But that was not that was a bit unique, and unless plastics in the equation, I don't know that we would call ourselves the experts for that.
Yeah,
we're not the experts for that. So
another question here is, what is the pull strength we get compared to other methods? So strength of laser versus others. So
sometimes it can be up into the 80-90% range. We typically say to design for 70%
parent material
strength. So you can do that a couple different ways. You can increase the width at the weld rib. Well, that's the main way to do that. So, and that's how vibration welding, I think they usually design for 150% of wall thickness at the weld rib. So it's not quite that bad, but yeah, it's probably on par with, I would say, ultrasonics, maybe hot plate welding. Hot plate welding's pretty darn strong if you're doing like a polypropylene. So.
Let's see. Oh, this is incredible welding technology for plastics. Thank you for sharing it. You're welcome, Juan. Thanks for joining. Any other questions before we sign off? If you think of them after the fact, we'll be sending out a follow-up email, as I mentioned. I should turn this to me. We'll be sending out a follow-up email with the recording of this webinar and then also the PDF of all the slides. And I might even throw in the compatibility chart and the design guidelines since we were talking about that as well. So, and you can just reply to that email with whatever questions you thought of. If you would like for us to have a meeting with just your company and you want to bring in a bunch of engineers or whoever else from your group, because you were the only one to attend and you're like, everybody in my group needs to hear this. We're all about that. So let us know and we would be happy to schedule that with you. Any other questions? I don't think so.
That's it, Jason.
Okay. Well then for now, we will say Goodbye. Thank you all for joining, and have a great rest of your day.